Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1925, Wolfgang Pauli introduced a principle that would reshape our understanding of matter, the exclusion principle. His paper, on the relation between the completion of electron groups in atoms with complex structure, responded to a crisis in atomic physics, a field struggling to reconcile experimental observations with existing theoretical models. This essay dissects Pauli's groundbreaking work, tracing its origins, detailing its core claims, examining its immediate impact, and highlighting its lasting legacy in the realm of quantum mechanics. The early 20th century witnessed a revolution in physics, spearheaded by Niels Bohr's model of the atom. Bohr's model, with its quantized energy levels, successfully explained the hydrogen spectrum. However, it faltered when applied to more complex atoms. The Zeeman effect, describing the splitting of spectral lines in the presence of a magnetic field, presented further challenges. The anomalous Zeeman effect, observed in many atoms, defied explanation under the existing quantum rules. These anomalies suggested a hidden degree of freedom, a missing piece in the atomic puzzle. Prior attempts to refine the Bohr model, most notably the Bohr-Sommerfeld model, introduced elliptical orbits and additional quantum numbers. This approach achieved some success in explaining fine structure in atomic spectra, yet it continued to struggle with the anomalous Zeeman effect and the structure of the periodic table. The number of possible electron configurations predicted by the Bohr-Sommerfeld model far exceeded what was observed in nature. Atoms appeared to prefer certain configurations, leading to the chemical periodicity observed by Mendeleev. An ad hoc rule was palpably necessary to restrict the possibles. Pauli's exclusion principle, initially presented as a bold assertion, offered a solution. He proposed that no two electrons in an atom could occupy the same quantum state. In other words, no two electrons could possess an identical set of four quantum numbers. The first three quantum numbers, n, l, and m, described the electron's energy level, angular momentum, and the orientation of its angular momentum in space, respectively. Pauli postulated the existence of a fourth quantum number, one that could take on only two values. This fourth quantum number, later identified as spin, provided the crucial missing ingredient. The exclusion principle proposed a direct link to the structure of the periodic table. Each electron shell, characterized by the principal quantum number n, could hold only a limited number of electrons. For n equals 1, only two electrons could occupy the shell, one with spin up and the other with spin down. For n equals 2, 8 electrons are allowed, and so on. This restriction explained the observed filling of electron shells and the periodicity of chemical properties. The noble gases, with their completely filled electron shells, exhibited chemical inertness due to their stable electron configurations. In essence, Pauli was presenting a novel constraint to limit the number of electrons with particular quantum. Now, Pauli's intellectual debt to Arnold Sommerfeld is clearly evident. Sommerfeld's work on the quantization of atomic energy levels provided the foundation upon which Pauli built his exclusion principle. Sommerfeld's introduction of quantum numbers to describe electron orbits and their orientations paved the way for Pauli's addition of a fourth quantum number. Furthermore, experimental data from the Zeeman effect, meticulously collected and analyzed by numerous physicists, supplied the empirical underpinning for Pauli's theoretical leap. These observations highlighted the need for an additional quantum number to fully characterize the state of an electron in an atom. While the exclusion principle offered an appealing explanation for the periodic table and the anomalous Zeeman effect, it initially lacked a theoretical foundation. It stood, in essence, as an ad hoc rule, albeit one with remarkable predictive power. The principle faced skepticism from some physicists, who viewed it as an unsubstantiated constraint on electron behavior. The underlying reason for the exclusion principle remained a mystery, awaiting a deeper understanding of quantum mechanics and the nature of the remainder of this discussion will delve into the substance of Pauli's 1925 paper, meticulously analyzing the impact of the exclusion principle on the understanding of atomic spectra, detailing the evolution of the fourth quantum number, examining the empirical evidence supporting Pauli's assertion, tracing the influence of Pauli's work on the development of Fermi-Dirac statistics, and highlighting the enduring legacy of the exclusion principle in disparate fields of physics. Pauli's insightful contribution transformed the understanding of the structure of matter, becoming a cornerstone of modern physics. The exclusion principle, born from the need to resolve anomalies in atomic spectra, provided a framework for understanding the periodic table and the behavior of electrons in atoms. While initially an ad hoc rule, it was later grounded in the deeper principles of quantum mechanics, securing its status as one of the most fundamental laws of nature. Pauli's groundbreaking 1925 paper on relation between the completion of electron groups in atoms with complex structure presented the exclusion principle a profoundly influential concept that revolutionized atomic physics. Initially conceived as a rule to explain observed spectral patterns, it became recognized as a fundamental law governing the behavior of fermions. Pauli's work provided a novel framework for interpreting atomic structure, chemical behavior and organization of the periodic table. The exclusion principle emerged from the effort to reconcile perplexing aspects of atomic spectra. Prior to Pauli's work, the Bohr-Sommerfeld model, while successful in explaining the hydrogen atom, struggled with more complex atoms. Spectroscopic data revealed that electrons in multi-electron atoms exhibited energy levels and transitions which the existing quantum framework could not adequately explain. There were anomalies in the Zeeman effect, where spectral lines split under the influence of an external magnetic field that defied conventional explanations based on three quantum numbers. The existing three quantum numbers designate the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. These numbers appeared inadequate to fully describe the quantum states of electrons in complex atoms. Pauli recognized the need for an additional constraint. Pauli's exclusion principle states that two identical fermions, such as electrons, can never occupy the identical quantum state simultaneously. In his 1925 paper, Pauli proposed the existence of a fourth quantum number, in addition to the three already known. This fourth quantum number could take on two possible values. These values, along with the first three quantum numbers, would fully define the state of an electron within an atom. The exclusion principle dictates that each electron must have a unique set of these four quantum numbers. This restriction limits the number of electrons that can occupy a specific energy level or orbital, thereby explaining the observed structure of the periodic table. The introduction of the fourth quantum number, later identified with electron spin, proved crucial in resolving the anomalies in the Zeeman effect. Spin accounts for the intrinsic angular momentum of an electron. It possesses a magnetic dipole moment. This intrinsic angular momentum interacts with an external magnetic field, producing the observed splitting of spectral lines. By incorporating the spin quantum number into the description of atomic states, the Zeeman effect became fully explicable within the new framework of quantum mechanics. Empirical evidence supporting Pauli's exclusion principle rapidly accumulated after its publication. Spectroscopists found that the observed spectral patterns aligned precisely with the predictions made by the exclusion principle. The principle explained the filling of electron shells in atoms, predicting the chemical properties of elements based on their electronic configurations. Calculations based on the exclusion principle accurately predicted ionization energies, atomic sizes, and other physical properties of elements. Pauli's work profoundly influenced the development of Fermi-Dirac statistics. This set of statistics governs the behavior of identical fermions. In 1926, Enrico Fermi and Paul Dirac independently developed a statistical mechanics framework based on the exclusion principle. Fermi-Dirac statistics describe the distribution of fermions among energy levels in a system at thermal equilibrium. They are crucial for understanding the behavior of electrons in metals, semiconductors and other materials. A direct impact of Pauli's exclusion principle lies in its ability to explain the structure of the periodic table and the nature of chemical bonding. The electronic configuration of elements, dictated by the filling of electron shells according to the exclusion principle, determines their chemical properties. For instance, carbon possesses an electronic configuration of 1s squared, 2s squared, 2p squared. The four valence electrons give rise to its tetravalent nature. This explains its ability to form complex molecules. Similarly, the reactivity of alkali metals arises from their single valence electron, whereas noble gases are inert due to their completely filled electron shells. The exclusion principle is a consequence of the spin statistics theorem, a fundamental result in quantum field theory. The spin statistics theorem dictates that particles with half-integer spin, fermions, must obey Fermi-Dirac statistics and exhibit antisymmetric wave functions under particle exchange. Particles with integer spin, osons, must obey Bose-Einstein statistics and exhibit symmetric wave functions. The proof of the spin statistics theorem relies on relativistic quantum field theory and causality, demonstrating that the exclusion principle is deeply rooted in essential principles of physics. The exclusion principle remains relevant across many areas of modern physics. In condensed matter physics, it explains the stability of matter. It governs the behavior of electrons in solids. In nuclear physics, it explains the structure of atomic nuclei. The exclusion principle influences the arrangement of nucleons, protons, neutrons within the nuke. Pauli's exclusion principle stands as a high point in the history of quantum mechanics. Its impact on understanding the structure of matter and the behavior of quantum systems is profound and continuing. It is a vital component of the standard model of particle physics, deeply integrated into the fabric of modern scientific understanding.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.